All right, so we're trying to differentiate this, right? So we're doing the quotient rule. We looked at the derivative of the numerator, derivative of the denominator is what we're at now, right? Now, this is where we like to have it written in that form, because how do we handle it? What do we bring out front? Bring that x1 down, right? Sorry, I don't know why I have it as negative. Jump a step ahead, sorry, y'all. Now, what do you have to be careful of this one, though, when after we're doing the power rule? This is a tough one in that sense. Yeah, so be careful with this one to see that, hey, the derivative of 7 minus x actually isn't just 1, but -1. So we want to be careful there with this one. Make sure that we have that represented properly using the chain. So this is one of those things, like I mentioned before in the previous days, that, hey, always double check the chain. Sometimes it sneaks in there, okay? What is someone using to help remember the quotient? More. Using to remember the quotient. My favorite way to remember it is low times the derivative of top, so low d high minus high d low all over low squared. Which is kind of nice, since there was a square in the denominator, make sure you see there, hey, I can just put it as 7 minus x. I don't have to write that with a square on it. So low d high minus high d low all over low squared. Now, as far as cleaning this up, the one thing I would say is you can multiply top and bottom by the square root of 7 minus x. The point behind doing that is to get rid of this. That's technically a complex fraction. So in this case, we really do not want to have a negative exponent there. But before we move forward, does everyone understand that this is the derivative we're looking at? Any concerns with where we're getting this from? All right, so as far as this is concerned, the main thing we want from a simplifying perspective right now is to say, I do not want that negative exponent. So I'm going to multiply top and bottom by the positive of that. Okay. What that's going to allow me to do is distribute this to both of our terms. All right, I would also say to make sure you multiply by 2 times that, just to make it even more straightforward. That way we can get rid of that 1/2 as well when I look at it. Okay, because we have a 1/2 here, we're going to multiply by 2 on top and bottom. Because this has a negative exponent, though, that's definitely why I'm dealing with it in this perspective. But just make sure to see again up here at the top, we're going to distribute it to both terms. With that in place, this first term will have 6x times 7 minus x, because the square root times the square root is going to be the same. But instead of 6, we should have 12. All right. When I distribute this here, 2 times 6 is where the 12 is coming from. But a square root times itself, hey, I could just take that without the radical. Question? We're trying to get rid of the fraction that's up here. We don't want those fractions. So that's why we're doing that. At that point, though, this is completely focused on simplification. Okay. Yep.
You want keep going like this or you want?
Yeah, you should be simplifying. Should definitely be trying to simplify. Okay. Now, keep in mind, there's different problems like this where, hey, it was just a polynomial on the top. Remember, multiply the polynomial in the numerator. You don't have to multiply polynomials in the denominator. Here, we multiplied this out because it was nice. Hey, it's squared. I can just put 7 minus x. Okay. But we definitely need to clean this up here. But as far as the work is concerned, we found it from here on out. It's just simplifying, right? So we've done half the work. With that said, though, make sure you see when we multiply this here, that's going to get rid of all of that right there for us. That's gone. Just be careful to make sure to see that that was a negative. So I'm going to put plus 3x squared minus 5 all over. Oops. 7 minus x now to the 3/2. I had 1 whole plus another half is where the 3/2 is coming from. And don't forget your 2 in the denominator as well. The nice thing about it is the multiplication works nicely with the term that had the fractions that we're trying to get rid of. Just be careful to see that it was a -1. Where did I get the, oh yeah. This negative here came from our chain rule, so we don't want to drop that off. So that's definitely an important piece that we need to have involved. Okay, which is kind of nice because at that point, plus and just copy down the fact. Then from there, all we need to do is distribute here. 84x minus 12x squared. So this will give us minus 9x squared plus 84x minus 5 all over 2 times 7 minus x to the negative, not negative, sorry, to the 3/2. Hopefully what you see is stuff still works out nicely because it all came from the same starting place, right? So as far as simplification, it doesn't necessarily create random outcomes. They are connected still, all right? Now, make sure, as mentioned, the reason that we're doing this is because of this right here. We didn't want those fractions within a fraction, right? We like to simplify what we call complex fractions. So I use multiplication to get rid of those fractions. Make sure you also see the nice thing about that multiplication is when I do that multiplication, this no longer had a fraction. I just took the factor as it was, okay? The one thing I mentioned, the reason I just put plus is because of the negative from the chain rule. Instead of subtracting like we were supposed to, that negative made it plus, I can move forward. This piece here, be careful though to see that it's no longer 6x because of the 2 that we multiplied by. All right, this is no longer a square root because I multiplied by that same exact factor. So that's why this became 12x times the 7 minus x. Okay. Any questions, concerns I can help with as far as cleaning that up? Is that going to be every single problem on the test? All right. I'm gonna have time to do other ones, right? And expect a quotient, expect a product rule, expect to have to use a chain rule somewhere, expect an application problem or two. Okay. Remember, as I mentioned, you definitely have a tangent line problem where we need to find the slope of a tangent line and then the equation of a tangent line. Those type of problems you definitely want to be ready for. Hopefully what you see in the practice test is I kind of try to put it all together as what we saw before. Now, the one thing I will say, as far as time-wise on this test, I would love us to practice a graph just to make sure we could see what the tangent lines on the graph in person. I don't think time-wise that's going to work in a 50-minute class. So just make sure you definitely look at the practice test so you know what is going to be on future test. Okay, that's definitely going to be a part of future test. Okay, the graphing of it. That was one of the reasons, though, I gave us that lab assignment on Friday. Now, remember, if you haven't done that yet, it's due tonight by 11. Okay. And there's no reason to not do it, especially given, what did I say about it? It's bonus points, so there's no point in not doing it. It's both here to help us with our test coming up, but also I'm gonna put his bonus points towards the test, towards the exam, sorry. Is there anything though I can answer as far as this one of someone?
So just to, the second by the dip of the first, right?
Yeah, it's,
Minus,
well, it's low times the derivative of high, so low D high, minus high D low.
okay,
So it's low D high minus high D low. All over low squared.
and whenever we squared it, so, that by two is,
Yeah,
okay,
since it was a square root, technically speaking, we probably should have a square absolute value on there. But when you need that stuff, we can deal with it later. Okay, so understand I'm not properly using this right now. But given the fact that we started with the square root, I think we could possibly say that we didn't want certain outcomes anyways, right? So there's certain things here that we can just take for granted. But technically speaking, we should have an absolute value here, but those are things, as long as we can simplify it, we can deal with later if we need, okay? Any other questions though, before we move on to that second one? We feel okay with the quotient rule then? All right, so here's one where I set it up for the product rule. Understand you could simplify this and just use the sum of difference in powers rules, okay? But as far as going through this again, my intent was just to practice using the product rule. Are we good if I get those derivatives of each factor individually? I guess technically what I should have wrote here though. Just to express the chain rule there, because the chain rule is getting done, it just happens to be derivative of x is just one, okay? Any concerns there? How do we build the product rule then, whenever I have something being multiplied together like we have here? All right. Not necessarily, as long as you have one original function times a derivative plus the other original function and the other's derivative, right? As long as you flip flop. So one term better have f of x and the derivative of g of x, the other one better have g of x and derivative of f of x. Okay. So as we jump into this problem a little bit further, this is where we got to go in and clean it up. So make sure you see here that we are going to be able to multiply these out. Okay. Use your foiling there, use your box method, whatever you're comfortable with. Make sure you see this one's definitely a little bit nicer as far as the simplifying is concerned, but we're definitely going to want to simplify these, okay? Now, should we be surprised that when we're done simplifying here, that we're getting a quadratic? Should we be surprised by the fact that we have x squared here when we're done? How many factors do we have up here? There's three, right? There's two unique factors, right? But remember, this is called multiplicity. So, hey, I'm counting 1, 2, and then 3, okay? Two unique factors, but three, the degree of that polynomial 3, right? Hey, well, the degree of a third degree polynomial will give us a quadratic or a second degree polynomial, right? So as we look at that, that's definitely like, okay, hey, definitely should have been expecting a quadratic here, okay? Any concerns with the product rule or simplifying that? Hopefully what you see is just good examples of some problems to be ready for. Product rule, radicals, quotient rule, chain rule is definitely something we want to work on. Hopefully you saw the lab assignment that I gave you, the three functions. I tried to mix it up as much as I could. Please understand with that lab assignment, the two graphs, you should be able to get a pretty accurate graph based on stuff you learned in college algebra. So if you need to, go back and look up some of that stuff as far as how to get that graph. The third graph, as I was doing by hand, it just plot the points out, just start plugging in numbers to plot the points out. What I encourage you to do is always check your domain first, okay? There's gonna be some of these problems that there's no point in going to a certain number, like negative numbers doesn't always matter for us, okay? So there might be situations where we have to be careful of. Now, with that moving forward, let's take that function to go a little bit further with it. Okay, so make sure you see here, I have this graph, this function that we just took the derivative of. I'm gonna keep that derivative so we don't have to rework it, so please keep in mind that this is coming from the work that we just did. Follow me on that? Any concerns with that being connected back to this function here? Now, what's happening though is I want to go a little bit further with it now, right? Hey, we got the function, we got its derivative. Let's go find the slope of the tangent line at x equals -2. And in fact, we're going to do three things, okay? We're going to do all three of these things that you see here. First, we're going to find the slope of the tangent line at x equals to -2. Then we're going to answer the question, when does the slope of a tangent line, I should say, equal -8? Okay. And then it's the last one we're going to look at here is let's find all horizontal tangents. Okay. Now, as we go through here, make sure to go back to this fact that we've already done the work to get the derivative of this function. That's the first thing you have to do to be able to answer anything with a tangent line. I need to get the derivative of my function. Okay. With that said, if I'm looking at this piece here, where we're just trying to find the slope of a tangent line when x is equal to -2. What is going on here, y'all? Let's get rid of this. Let's do that. What do I need to do to go find that slope? Plug in -2 where? Into the derivative. Good. That's definitely an important thing. You always want to read. What should I be working with? That's going to be one of the application problems, as I kind of mentioned, is read what it wants you to plug into so that you're making sure to go to the correct function. So here we're going to plug in this -2 into this function. Now, as I've shown before, this would be where I like to jump into my synthetic division, sorry. Make sure you let me know if you guys agree with 8. Now, what does this 8 represent? It's the rate of change at -2. Okay, this is the rate of change at -2. Which would be the slope of a tangent line there as well. Okay, if you wanted to find the equation of the tangent line, what else would we need to go do? I just asked for the slope here, but let's make sure we're comfortable with that too. In order to find the equation, We have the slope. What else do we need? You could get the y-intercept, but that's gonna be tougher without just some point to start with. Okay, so make sure you look here. We can pull up the graph. Okay, this is the graph that we're looking at for this function. Okay. We can zoom our graph in to where x is -2. Okay. And if you look here, let me erase something. I didn't know I was gonna do that. Sorry. This is the point for the function when x is -2 right there. Okay. If we look at this slope is pretty steep if we think about a tangent line, right? So it looks like, hey, that I could see where that 8 is coming from. And then we also know it's positive because it's increasing there, right? That was one of the other things we talked about. But whenever we want to find the equation of a line, this point is very important. Okay. Where do I need to plug the -2 in though to get to that value, which looks like it should be 16? Right? The original function, right? So this would be a situation where like, hey, once I get my tangent, I'm going to plug the -2 into the original function to then try to find what's going on there. Everyone follow me with that? Now, with that said, let's shrink this graph back down, get it out of the way. Now, as you saw from the graph, we definitely should be expecting this to equal -16, okay? Oops. Which -4 squared is 16 times 1. Okay, we definitely get that agreement. Just make sure to see here, this is where you would go into point slope form. Y minus 16 equals 8 times x plus 2. There's supposed to be subtraction there because we plugged in -2. That's why it's x plus 2. Okay. As far as software is concerned, expect to have to solve for y there and put it in slope intercept form. But are we okay with putting it in that form to get the equation? What we call point slope form? Any concerns there? Now, remember, the key that you need to see here is that, hey, when I plug into my derivative, it's going to give me the rate of change at that value, which is also the slope of the tangent line. Okay. When I go forward with that, if I ever need the equation, I then take the slope that we just found the derivative, and I need to go back to the original function to get the point that's at that specific location of the graph as well. So that's why we have to plug the -2 in there. Okay. The graph here, as we saw, showed we should be expecting 16. So that was kind of nice. Okay. Once we have both those pieces, that's where we go use the point slope form, and that's going to give us a linear equation for that tangent line right there. Okay. All you need to do at that point is get y by itself. So distribute the 8, add 16 to both sides. Any questions with that? Everyone's good with getting the point and slope separately from the two different functions? All right. So as we go over here to this problem here, now I changed up the question a little bit, right? Now the focus is not just finding the slope at a specific x value, but we want to find when the slope is -8. So what are we setting equal to -8 at this point? F prime of x, right? This is what I want us to do at this point is, so let's go find when the rate of change is -8. Now, this is just more about practicing and making sure we interpret what's going on as far as information is concerned. That horizontal one is going to be a little bit more important moving forward, okay? I just picked this one because it's going to be a nice one to solve, all right? But it's also getting to the point just, hey, make sure to realize, hey, I want to set the derivative equal to 0 now. Not 0, sorry, derivative equal to -8. So we're going to go in here and say, hey, when does 3x squared minus 2x minus 8 equal -8? All right, well, we got to do some work to solve there, right? I understand you might be able to look at it and catch one of those, but that's not going to be the only one, right? How do we solve this? Let's get all solutions. All right, where are you getting that from though? What do we have to do? That's my question. But first we have to make sure get it equal to what? Yeah, so make sure you see here, don't forget the little steps, right? By adding the 8 to both sides, now it's equal to 0. That's the key. Once I get it to equal to 0, now we go into our factoring skill. So as mentioned, make sure you, as you saw there, we could factor out an X. So one of those solutions that you may have caught right off the way is definitely 0. I don't disagree with that, but we also want to make sure to show here that like, hey, 2/3 is another solution. Okay. So if I look here in my graph, oh my goodness. Whatever. It's not working. I don't know what's going on. If you looked at your graph though, you should see that these two solutions are going to occur about right here and right here. Okay, and that's going to be something that when we look at the next section of the course, we'll be able to start talking a little bit about. This graph isn't symmetrical in the sense of, even or odd, but we have a special point in between where the rate of change is changing itself. Okay, so here and here, there is some type of symmetry. Okay, almost like how you look here and here, that was kind of not the same in the sense of both of them were 8, but one side was 8 and the other side was -8, right? So there was some kind of symmetry that took place there that we can talk about. Okay. And that's a lot of stuff we're going to start digging into next week when we start going beyond just find a derivative and make sure to know how to get a rate of change. Let's start to describe functions using this as well. Okay. Are we all good though with where the 0 and the 2/3 is coming from? What would we get if we plug 0 2/3 into the derivative function? So if I took one of these and I plugged it in for X, what would it equal? Mhm. The whole point with doing that to see is when would it equal -8? Well, I know these two values, that's when it would equal -8. Okay. Any questions that before we go to the other one, the horizontal tangents? All right, so the next one then that we're gonna look at is using the same thing. Taking the same function, taking the same derivative that we found. We want to find where this graph has horizontal tangents. Okay. Now remember, as far as tangents are concerned, we're looking at stuff like, hey, this was a tangent line because we took the graph and we found a line that matched the rate of change at a specific point. Okay. This line had a slope though. What was the slope of this line that we found with the first part? We'll go back to the first part. What was the slope? It was 8, right? That slope was 8. This line though is increasing because it has a slope of +8. What does a line look like if it's horizontal, right? Well, if I go over here and draw a horizontal line, it would look something like this. We all agree with that? Now, where would I have to put this line for it to be what we call a horizontal tangent is what we're looking at, okay? What I hope that you see here is anywhere a graph turns, then that's what we're trying to find right there. Okay. Now, yes, it crosses over here where we're kind of ignoring that for a second and we're focusing on single points. Okay. So at that area of the graph, it's a horizontal tangent. Now, that also goes back to remember when I talked about tangents, it's about the local areas. Like if I zoomed in on this graph as much as I could, it's no longer letting me zoom though, sorry. We would see kind of that graph mimicking what's going on. And the further we zoom in, the closer that line actually matches the graph itself. Okay. What you'll find here though is that a horizontal line also has a slope of what? Of 0. Okay, so whenever we say horizontal tangent, hey, that's what I'm looking like at a horizontal line, but the key here is a horizontal line has a slope of 0. So if I want to find all horizontal tangents of a function, what do I have to set the derivative equal to? Everyone's comfortable with that? Now, hopefully what you see, we'll do the same thing we did before. The nice thing about this, though, our function's already set equal to 0. So what are some ways we can solve this one? Make sure we review this because we've been more focused on derivatives for a while instead of solving stuff.
Good factor.
Factoring is what I recommend, right? If you forget how to factor for a second, though, what else could you use here?
Add, 8 to both sides.
I wouldn't complete the square here. That's the only reason you would add a is complete the square, but because a is 3, that would make that a pretty tedious process. Okay. But understand, like with that said, knowing that this is a equal to 3, b equal to -2, c equal to -8 will help you in any process you choose. But what's one thing with quadratics that we should have memorized? Quadratic formula, right? So if you forget how to factor, make sure you go back to the quadratic formula. Okay. The nice thing about this is a times c is what, -24, right? Well, if you break that down to 6 and 4, -6 plus 4, what does that give us? -2. So this is definitely factorable, right? So if you remember back at the kind of the first week of class, I talked about how I like to write it like this. And we can show that -6 and 4 will satisfy both of those. Okay, so factoring is definitely something you're going to want to use. And we'll get to these factors here. Now, whatever way you're comfortable with factoring, make sure you go back and practice that. But also make sure you go look at the quadratic formula that you have ready to go. Because if you forget factoring, that's a way that would give us our solutions here as well. It's just more work than needed in this case. Okay. Now, with that said, what could have been a hint that x minus 2 was a factor here? Why would you say this would tell us it's possibly a factor here? Because it was squared, right? Anytime you have something that's in factored form and one of the pieces was squared, I should expect that to be a factor in my derivative as well. So that could be some way to kind of help you remind you, like, hey, I shouldn't be surprised to see x minus 2 here when I'm doing my factor, okay? Now, with that said, though, make sure you go and set these each equal to 0. Be careful not to forget your negative on the 3x plus 4, though. Redo this graph so we can zoom in and make sure we see where we're getting this from. Adding or subtracting the 4 from both sides. So remember here, we set each of these equal to 0. When we add subtract the 4 from both sides, it makes it -4, and then we divide by 3. Now, if I zoom into this piece here, I know we can't see the x-axis. It's not as nice, but remember, we know that -2 is this one based on the fact that we just looked at it. Okay. This over here then is going to be -1. Which of these values is between -1 and -2? If this is -1, this is -2. Well, that's -1 and 1/3, right? Okay. What is going on at this point again that made it as something we wanted to focus on? Well, if we draw the tangent line, this is where we get a horizontal tangent line. Okay. We all comfortable with where that's coming from there? Now, the nice thing about the 2, if I zoom this graph out, scroll down some. Where does that one occur at? which is an x-intercept though, right? You everyone see how it was an x-intercept, going back to the fact that like, hey, this was a part of the original function as a factored squared. When I took the derivative, hey, look, it was still a factor, okay?
So if it's a whole number, does that mean that it will most likely be at like the origin mark, like a,
No, not necessarily. It just, that has everything to do with this piece here,
oh, okay,
okay? Like even if you go back to when we did the derivative itself, we could have factored out now instead of simplifying the way we did. I didn't do it that way because simplifying is a bit more of a direct approach. But if we look at this here, this is 2 times x minus 2, right? So what I could have done is said, hey, I could pull out an x minus 2 here. That would give me x minus 2 plus x plus 3 times the leftover 2. Okay. Well, that would give me 2x here plus an x, so that's where the 3x comes from. And then we had the minus 2, and 2 times 3 is 6, so that's where the plus 4 comes from. Well, hey, that was the exact factor that we did earlier. So you could have saved yourself a lot of work by just factoring it from the beginning, but you may not have caught that right away that that was the same thing once I take a 2 out, right? So that's not something I would say you would have to do, okay? That goes back to the fact that, hey, this was squared. That's why that was allowed to happen. So really, anytime I put an exponent on there, we should expect something special at that, okay? Because it was an x-intercept of the real original function, yes, we can expect them,
Mhm.
okay? Does that help with that? Whereas this one, yes, it was an x-intercept, but then it disappeared as I went through the work, so I didn't worry about that, okay? Any other questions or concerns I can help with? Now, as we close out today, what were we trying to find when we set the derivative equal to 0? Horizontal tangents, right? Does everyone see that? Now, the nice thing about that is when we're able to differentiate a function, that's going to give us where it's turning. That's why we like horizontal tangents. We can start to find where a function turns. Okay. Now, with that case, though, we go to the first derivative for tangents. Okay. So make sure you see that there. We can do other derivatives, but this would be unique to the first derivative. Okay. We'll have to talk about what to do with the second derivative next week. Like, how can we use it? One of the things we'll look at is like how a ball's dropped. You'll have velocity and acceleration. Both of those impact the situation, right? For us here, I only looked at the first derivative to get those rates of change. Okay. Any questions, concerns though, as we finish up today? All right. So my one thing that I remind you again is that have to scan that sheet to a PDF and make sure you